Hey again, let's pick up where we left off, which was me saying let's look more at the difference between what we measure in our sample and what's true in the full population. And saying, like, think about a full population where 60% of the population votes Democratic. How likely is it that if we take a poll of 100 voters, between 50 and 70 of them vote Democrat? So, how likely is it that our sample proportion will turn out to be within 10% of the population proportion? Or what's the probability that the sample mean approximates the population mean? And I said answering that question starts with building a confidence interval around the test statistic. In this case, our test statistic is the proportion of voters who vote Democratic. When our sample is unbiased, then we can estimate the sample mean and the standard deviation. So we can know the central value in the sample, and we can also know how widely spread out or dispersed the rest of the values are. Quick side note, if the sample is biased, then the mean and the standard deviation are also biased, which means we can't learn anything about the full population. And that's why unbiasedness and avoiding selection bias in data collection are so important, and why I've hammered on those so much through the semester. All right, so we have the mean and the standard deviation of the sample, but those are statistics. Those are not facts, right? In other words, the sample mean and standard deviation are not a perfect mirror to the full population. And what we really want to know is not the proportion who vote Democratic in the sample. We want to know the proportion who vote Democratic in the full population, right? We know that here it's 60%, only because this is the imaginary world living in my head. Like, in real life, we don't know that. And so we want to know how sure we are that the proportion we see in the sample is the same as or pretty close to the proportion that exists in the full population. The confidence interval does that for us. It tells us how confident we are that our test statistic correctly infers the true relationship in the full population. And it does that by answering the question, what is the probability that the sample mean approximates the population mean? To get the confidence interval, we first have to identify an appropriate level of confidence. I talked a little bit about what confidence means in the first mini lecture for this week. Let me clarify that and drill down into it a little bit more here. So a confidence interval is a range of values that we're fairly sure contains the true values, or a range of values that we're fairly sure our true value lies within. In other words, it's a range of values that's likely to include the true population value with a certain degree of confidence. It's usually expressed as a percentage, where we are X% certain that the population mean lies between this value on the low end, that's the lower bound or limit, and this other value on the high end, that's the upper bound or limit. In political science, we usually use a 95% confidence interval. And strictly speaking, a 95% confidence interval means that if we were to take 100 different samples and then compute a 95% confidence interval for each sample, then approximately 95 of 100 confidence intervals will contain the true mean value. A confidence interval of 95% means if we took 100 different samples and computed a 95% confidence interval for each sample, then approximately 95 out of those 100 calculated confidence intervals will contain the true mean value. So we will be right, or our range will be right, 95 out of 100 times. And if that is true, then we would say the relationship is statistically significant at the 95% level, or with 95% confidence or certainty. So when we say a relationship is 95% statistically significant, we mean in 95 out of 100 samples and sample rounds of this thing we're doing now, in 95 out of 100 of those, the true mean value is going to be in the approximated confidence interval. Practically speaking, when you're looking at data output or you're looking at a data table in an article, you want to set a level of significance that is high enough to have confidence, like reasonable confidence, that what we see in the sample is what exists in the full population. And again, in political science, we usually use 95%, though we also will talk about variables if they're statistically significant at 90%. Okay, so we choose our level of significance, usually it's 95%. And then we want to differentiate the variables that are significant at that 95% level from the ones that are not significant at that 95% level. Or we want to differentiate the ones where our certainty in significance, our certainty that we will be right, is 95% out of 100, 95 times out of 100 or higher, or 94 times out of 100 or lower. And again, all of this is because we are inferring unknown population parameters like the mean and the standard deviation. We're inferring those about the population from a known sample. And so through our statistical analysis, we're determining whether the relationship we're seeing in the sample is mathematically strong enough for us to believe that it also exists in the population. That's the probability. If it is, then we can draw conclusions about the relationships we see in the sample. But if it is not, then we conclude that there is no discernible relationship between the independent and dependent variables, and we say the result is not statistically significant, and our hypothesis is not finding any support in our data. So how do you actually determine whether a certain relationship is statistically significant? Well, in Stata or in other statistical software output, you're going to look for something called a p-value. Now, I don't have space in this course to get into the nitty-gritty details of the p-value, so let me give you instead what I think is a relatively simple way to think about it. 1 minus the p-value is your level of confidence that the relationship in your sample also exists in the full population. So on the slide, it says the p-values you're looking for are 0.1, 0.05, 0.01, and 0.001. And it says that the smaller the p-value, the more certain or sure you are of the relationship. So I said 1 minus the p-value. So take that first one. Take 1 minus 0.10. 1 minus 0.1 is 0.9. So with a p-value of 0.1, we can be 90% confident, right? 0.9, 90% confident that this relationship is statistically significant. Or we can say that this relationship is statistically significant with 90% confidence, meaning 90 out of 100 times the calculated confidence interval will contain the true population mean. Okay. Take 1 minus 0.05. So say the p-value you're looking for is 0.05. 1 minus 0.05 is 0.95. So when you have a p-value of 0.05, you can say that this relationship is statistically significant with 95% confidence. And that's what we saw on the distribution on the previous slide. With a p-value of 0.01, 1 minus 0.01 is 0.99. With a p-value of 0.01, you can claim statistical significance at the 99% level. With a p-value of 0.001 or lower, you can claim statistical significance with 99.9% confidence. So 99.9 out of 100 times, the true population mean will be within the calculated confidence interval. Okay. So when you're looking at data output, you're looking at p-values. In journal articles, or when we're writing up our research papers, we usually mark significance with little stars. Sometimes we put them, you'll see it in italics or in bold font, but really it's the stars that are most conventional. So here's an example from a paper that looks at all of the countries in the world and tries to understand why there are differences in country-level abortion allowances. So the dependent variable is allowances for abortion, and it ranges from 1 to 7, where the more provisions you have, the closer you get to a 7, right? If you have no allowance for abortion in your country, you're quoted a 1. And if you have full on-demand, no questions asked and no limitations access, you're coded as 7. The method of estimation is ordered logit, which is something we've not talked about yet, so kind of set it aside for next week multivariate analysis. But just know the purpose of this paper was to assess which was more important for explaining abortion liberalization or increased access to abortion. Was it structural explanations like regime type, level of democracy that is, and economic development and freedom of religion, so structural stuff? Or was it empowerment or agency explanations like women in government, women in the labor force, and the extent to which the country has adopted world values? So the question is, which is more powerful for helping us understand different countries having different levels of access to abortion? Is it the structures of the countries? Are they democratic? How economically developed are they, etc.? Or is it the extent to which women and other important actors are empowered as political agents? So the percentage of women in the government, the percentage of women in the labor force, etc. So each row has one of those variables. And the second column the second column reports the result of the ordered logit estimation. In other words, the second column has the statistical results. If you look at the bottom blue row, you see kind of a key to use in interpreting the little stars on some of the coefficient estimates. If you see 3 stars, that means the relationship marked with those 3 stars is statistically significant with a p-value of 0.01 or lower. In other words, 3 stars means the relationship between that variable and the dependent variable is statistically significant with at least 99% confidence. 2 stars marks a p-value of 0.05, meaning that that independent variable and the dependent variable are statistically significantly related with 1 minus 0.05, which is 95% confidence. And if you see 1 star, that marks a relationship with a p-value of 0.1, meaning that that independent variable and the dependent variable, which in this case is legal or liberalization of abortion, are statistically significantly related with 90% confidence. I'm not going to walk you through all of these results, but I do want to touch on a few of them. So let's look at the last 3 variables, starting with the percent of women in the labor force. The coefficient here is the coefficient here is 0.104, and there are 3 stars. The number of the coefficient doesn't matter for us right now, but the sign on it does, whether that number is positive or negative. The coefficient is positive, and it's marked with 3 stars. The positive sign means that there is a positive relationship, not normatively good positive, but statistically positive, so that as the percentage of women in the labor force increases, the country also has an increasing number of abortion allowances. That is, an increasing number of circumstances under which abortion is legal. And the 3 stars mean that relationship where a percent of women in the labor force increasing leads to an increase in abortion liberalization. That relationship exists in the full population with 99% certainty. Okay, looking at the next row down, the independent variable is the percent of Catholics in the country. The coefficient is negative, which means that there is a negative relationship between this independent variable and the dependent variable, which is number of abortion allowances or abortion liberalization. Again, negative doesn't mean normatively negative or bad. Negative means statistically negative, so that as one goes up, the other goes down. So as the percentage of the country that is Catholic increases, the level of abortion liberalization decreases, or the number of abortion allowances goes down. And again, this relationship has 3 stars, meaning that it is statistically significant with 99% confidence. Finally, let's look at the next row where the independent variable is CEDAW. That's the Convention on the Elimination of All Forms of Discrimination Against Women. It's an international treaty, and so this variable is measuring whether it's whether or not countries have signed and ratified this treaty, Convention on Elimination of All Forms of Discrimination Against Women. The estimated relationship is positive, which means countries that have ratified CEDAW so that has gone up from 0 to 1. Have they ratified and no to yes? Also have increasing numbers of abortion allowances in the sample. Positive coefficient means as one goes up, the other goes up. A negative coefficient means as one goes up, the other goes down. So in this case, it's positive, so ratifying CEDAW increases the number of abortion allowances in the sample. But see, there are no stars on that coefficient. That relationship is not statistically significant. That means that we cannot say with any credible level of certainty, this relationship we see in the sample also exists in the full population. Right? We cannot say that the p-value is going to be larger than 0.1. That relationship between CEDAW ratification and abortion allowances exists in the sample, but is statistically insignificant, meaning it doesn't also exist in the full population. Okay. Here is some stata output, and this is stata output of a regression looking at how different kinds of human rights abuse affect the number of protest events within a state against the government. The independent variables are political imprisonment, that is how many people are getting thrown in prison for their political views rather than breaking any kind of laws, torture, disappearances, and state-sponsored extrajudicial killing. So imprisonment for political views, torture, disappearances, and killing. Let's look first at the last one of these, which is in the 4th row on the table. This is killing. The coefficient is negative, so there is a negative or indirect relationship. As one goes up, the other goes down. As there is more killing, we see fewer protests. You can skip over the standard error, you can skip over the t-score, and look at the next highlighted value. That's the p-value. Remember that to find the level of confidence or significance, we subtract this value from 1. In this case, 1 minus 0.002 is 99.8. And so we can say killing reduces protest in the sample, and it also reduces protest in the population with 99.8% confidence. In a table, we would give this 3 stars because the p-value is less than 0.01. Now let's look at the estimated effect of torture. The coefficient here is positive, suggesting a direct or positive relationship. More torture leads to more protest. That's what's in the sample, right? But look at that p-value. The p-value is 0.395. 1 minus 0.395 is 0.605. So we can say that this relationship exists with 60.5% confidence, which is nothing I want to hang my hat or my career on, right? It means that 60% of the time, the confidence interval here is going to have the true value in it, and the other 40% of the time, it just won't be there. So we say that this relationship is statistically insignificant. It's below any of the conventional levels we're looking for, 90%, 95%, 99%. This is 60.5%. This relationship is statistically significant. We cannot infer anything about the full population from it, so we move on. All right, so why have we gone over all of this? Well, for all of our test statistics, we want to understand the magnitude of relationships. But we also want to understand if there is a statistically significant relationship. So we want to know how big or strong or powerful the relationship is and what direction it is in the sample. But we also want to know if we can infer or generalize from the sample to the full population, right? If we can't do that, then we say there's no relationship between the two variables. If we can do that, if we do find a statistically significant relationship, then we can move on to say how strong that statistically significant relationship is. And I'm going to pick up with our third mini lecture talking about how we can move from it is statistically significant to this is how strong that relationship is. Okay, so I will see you then.